Okay. Right. So we are looking at differential forms on Riemann surfaces, like last lecture. You remember? Okay. So one of the classes of forms that we discussed was this holomorphic one forms, right? Holomorphic one forms. So what are they? As we discussed, locally they are going to look like this. So locally they look like f of z dz, right? Where f of z is a holomorphic function. So this is like on u, maybe on coordinate chart u inside x. So x is our Riemann surface. They locally look like this, where f of z is holomorphic on u, holomorphic function on u. That belongs to, I don't know, the notation for holomorphic function. I can use maybe O of u if you don't complain. Just this is the part of the sheet of the holomorphic functions we will introduce later on, but I mean that's just notation. So these are holomorphic functions. U. I mean, the point is that you cannot globally write such a thing in this form, right? Because there is no global holomorphic function on x if x is compact. Well, unless constant functions. That's one problem. Another problem is that there is no dz on x. There's no one form dz on x. dz also is local. So everything is local. But once you allow yourself these local expressions, it's as a beautiful expression that you learn in complex analysis when you integrate things. You're integrating holomorphic functions, but you stick dz there for good reason. Okay, so we had a notation for this. So the notation was, as I told you, this is kind of unfortunate notation. So omega x. So this is a space of holomorphic one forms on the Riemann surface x. Holomorphic one forms on x, right? So obviously this space omega of x is a vector space over C, right? It's a complex vector space. So is a vector space over C, is a complex vector space. Now, what happens is that if X is compact, which is you're always assuming, we will show one way or the other, or we have to show that, so let me put it like this, we'll show that X compact then this space is finite dimensional, omega of x. The space of all holomorphic one forms on x is finite dimensional. And its dimension is an important invariant of the space. It's the genus of it. So that's what happens. And, okay, so being finite dimensional is already quite surprising. There's no reason for this to be finite dimensional. But then the next one is even more interesting, and dimension of omega x over C is equal to G of x, the genus of the surface. So it's quite a thing, right? I mean, you work with this sort of holomorphic differential forms, one forms, and then all of a sudden some topological invariants pop out. Of course, because of Duram theory that we discussed, this should not be too surprising for you, because in Duram theory, we know that all cohomology can be captured through Duram cohomology, which is essentially nothing but a space of closed forms by exact forms. But here you're just looking at it as just forms, not quotients. They're not in some cohomology class per se. They're just forms like that. So that's okay. Now let's look at some examples of this. Maybe just see if we can maybe verify this in some cases, or at least get an idea how.
Just 1 minute.
Yes.
I'm stopping. Sorry.
You're just you wanna.
Yeah, could I just look at it for a minute more?
Sure.
Thank you.
Okay, so but I'm going to erase top part, not the. Not. Okay, so let's look at some examples of this phenomenon. So example 1. So let's take x equal to P1, projective line. So we can try, yeah.
Sigma.
Hmm?
Dimension of omega x over sigma.
Let's see.
This is C.
Yeah.
Complex numbers, yeah. Right. So let's look at projective line. Now we may try to find some holomorphic one forms on the projective line. So what are the possibilities? I mean, let's try something, right? If you want to try something, let's look at, for example, omega equal to dz, for example. I mean, this certainly belongs to omega of P1 minus infinity, right? I mean, this is holomorphic everywhere, is a one form, and is defined on the plane, so it's nice. But the question is, can we extend it to a holomorphic one form to the whole P1? That's the question, right? Does it extend to the whole P1? The P1? Well, you don't know, but to address this question, we can just pick a coordinate at infinity and see the behavior of this function as a result, this one form as a result of going back to near zero, and see if we can extend it over there or not, right? So let's do that. If you just pick up a coordinate, okay, coordinate w equal to 1 over z, right? Which is z equal to 1 over w. So we bring things near zero, which is more understandable for us. So then the omega in this new coordinate system is equal to dz. Z is 1 over w. This is P of 1 over w is minus dw over w squared near zero. And you see that this blows up, okay? Near zero, it blows up. Okay, so what happens is that basically you see that this cannot extendable, right? So not extendable. At least for this omega equal to dz, we know that it cannot be extended. In fact, one of your assignments, assignment 1B, is to show that actually there is no non-zero holomorphic one form on P1. That's the assignment. So your assignment says that no holomorphic one form. I mean, no non-zero holomorphic one form on P1. I mean, the way to prove this is not very difficult. I give you a hint. You can just write it first in P1 minus infinity. So then you're going to get a function on dz, and then use this trick. You're going to basically show that there can't be any rational function. Instead of dz, if you put any rational function in front of this, still is not extended. So this problem persists. This problem is not removable in a way. So,
What if we pick a different coordinate?
sorry,
What if we pick a different coordinate?
infinite coordinates?
A different coordinate?
Same. You're going to say you're going to get not extended. Yeah. Yeah. It's enough to show that
Like what if we have W equals Z squared?
W equal to Z squared. Well, that's not the coordinate because that's 2 to 1.
Oh,
Yeah. You can choose maybe some other coordinates, but there are many zeros over it. But you see, if you show that in one coordinate is not extendable, you know that in any other coordinate is also not extendable.
right.
So this is a coordinate independent concept. So yeah. Okay, so that confirms our statement, right? Dimension of omega x. In other words, we just verified that dimension of omega p1 over c is equal to 0, which is genus of the p1. Well, that's what we have, right? So this is example 1. Any question?
Can you remind me again why we have to take away infinity there?
Because dz is not defined at infinity.
Oh, yeah.
Yeah, it's just we don't know how to define it at infinity. We try to define it at infinity by going into coordinate, bring it near z, and study it around z, but we see that it's still has a hole like that.
Okay. That's-
Exactly. Okay, so that's good. Any other question? No, that was a good question. Okay, now let's look at another question. So go one genus up, maybe on the torus, right? If you go to the torus, let's look at that. So the torus, the complex torus, one way to think of it is this lambda, where lambda subset of C is the lattice. I want to construct some omega belonging to omega of x. I want to construct some holomorphic one form here. Can you guess a holomorphic one form on the torus?
What's the identity?
What's that?
The identity.
Identity? Well, identity in what sense? It has to be a one form, right? So it should have dz or something like that. Yeah.
Constant.
Constant? Oh, constant what? But we need one form.
The C times the
dz, yeah, exactly. So let's take omega equal to dz. Now, we have to make sure we understand why this is a one form on Gaussian space, right? So we know that this is a one form on C for sure. Because over C we have global coordinates, and this is one form. This is a holomorphic one form, actually. This is a holomorphic one form. Holomorphic one form on C. But we are interested not in C, in the quotient of C by this lattice, right? In the quotient group. Now, what happens is that this one form is actually invariant under the lattice action. So it descends to the quotient. So just write it like this: since omega is invariant under lambda action, in the following sense, in the sense that d of, if you translate with any lattice element, or actually with anything, you're going to get the same thing because it's a constant, right? So it means that, so the situation is like this. You have this quotient here, C, Okay, this is a projection map. You have C over lambda. You have something which is here. You have I mean, you have an object that belongs here. In order to show that it descends to the quotient, you have to make sure that the object here is invariant under the action. Then it descends to the quotient.
So omega equals z squared dz is not invariant under the lattice action.
Yeah, that's an excellent point. So omega equal to, for example, z squared dz, you said. Well, exactly, that's not invariant, no. Because if you do this, you see that you're going to get a mess in front of it. You're not going to get the same bump form.
Okay.
So anything else you try is not going to work except with constant multiple of this dz. That's it. So this is indeed a holomorphic one form on C over lattice. Okay, and what happens is that actually dimension of omega of C torus is 1. In fact, I mean this we cannot prove now. We have to wait a little bit. Omega of C over lambda equal to 1. And this is the generator. You found the generator of this. Okay. So unlike the case of sphere, which was I mean projective line, which was easier to deal, this already has some difficulty to prove that this dimension is 1, which is of course the genus of this guy, right? Genus of C over 1. Okay, so in your assignment 1B, I gave one more thing to think about. So let me explain that. Actually, that's a good. Any question about this, by the way? I gave you another one form to work through. So this one was this is example 3. So this one was like x is a smooth affine curve, which was like this w squared. So y squared equal to p of x. So what is p of x? P of x is a degree n polynomial. P is equal to n. So let's take it at least 3. I mean, 2 is also okay. That's not a problem, but I'm going to take it at least 3 because that's very interesting thing to start. And P belongs to C of x. It's just a complex polynomial, right? Okay, now there was one condition that I insisted to have that condition in order to make sure that this defines a smooth affine curve. What was that condition? Do you remember the condition that I imposed?
Does not have repeated roots.
No repeated roots.
The derivative does not vanish.
What's that?
The partial derivatives don't. The derivative doesn't vanish.
Yeah, there is no point where both P of Z and P prime of Z are equal to 0. That's right, yeah. So basically with distinct roots, I just say. With distinct roots. Then, so what is this X? I mean, X is really the set of all X and Y, you remember, belonging to C2, such that Y2 is equal to Px. So we use the inverse function theorem to show that this is actually a smooth, non-compact Riemann surface, right? It's a smooth, I mean to say something is a smooth Riemann surface is an oxymoron. I mean, not oxymoron, it's redundant. We shouldn't say it, but sometimes I say these things. Okay, so this is like, let me say it again, smooth, non-compact Riemann surface. I mean, non-compact. So this is examples of that in my first lecture, I discussed this. They're called affine curves, right? It's an example of a smooth affine curve. Right? Okay, now we want to construct some differential forms, some holomorphic bond forms on this. Some holomorphic bond forms on this. And one of the things I suggested is to look at the following: omega equal to dx over y. Okay. So if you open papers of Abel, Jacobi, Riemann, you see this dx over y. Even Euler and all these guys, you see this expression dx over y. The classics would write it like this. Write it like dx over square root of p of x, e.g. for p of x equal to x minus lambda 1, x minus lambda 2, times x minus lambda 3. So you have this elliptic integral, for example, I mean, this form omega, you get equal to dx over the square root of, I don't know, x minus lambda 1, x minus lambda 2, x minus lambda 3, with distinct roots.
Why is it just simply equal? Why did you put the quotes?
Yes, I put this quote for the following reason. You see, this needs interpretation. Dx over root px needs interpretation. Because what is root px? Every complex number except 0 has two distinct roots. So which one you take?
You pick one.
Hmm?
Pick one. You just select one.
How do you make sure that then you get something holomorphic? Actually, it doesn't exist. There's no over the domain that's defined, it's not holomorphic. So that's not it. But this, now the part of the assignment is to show that this is actually a well-defined holomorphic one form all over X. Now, at all points where y is different from 0, where p of x is different from 0, this is obvious, right? Because you just divide. Okay, so let me tell you how to think about this, because it's indeed quite confusing. So let me tell you how to think about it. So we have this surface x, right? I'll just erase. Y2 equals to p of x. So we have two functions, the God-given functions defined on x, right? What are these two functions? There's this function x from x to c, sends x and y to x, right? And there is another function, y, also from x to c, that sends x and y into y. Right? I mean, these two functions exist. You don't have to take you don't have to extract roots or do anything funny. These functions, the way that now things are set up, the beauty of this curve, this object is that these two functions are there, and they are obviously holomorphic, or both holomorphic, right?
Don't we have the same problem with y? Because y squared is equal to p of x has two solutions.
We are not taking solutions. We are on the space of solutions, actually. So we are projecting a solution. The solution. So the point of this construction is that if you go upstairs to the space of all solutions, then this function y is defined there.
But it's a 2-to-1 function.
It's a 2-to-1 function, but 2-to-1 functions are fine. Extracting roots is a problem. The inverse function of 2-to-1 functions is a problem, right?
But isn't that what we're doing when we project down?
What do I mean by projecting down? Yeah, so you see, this is this C cross C. And your curve is here, like any other curve in like over, and you have this, let's see, You have these two coordinate functions, right? And they're holomorphic, nice. So when you do dx, you get a one form, you divide it by this function, but this function has to be non-zero. So omega is, this is completely trivial to see that omega is a one form on, so let me write, so now I'm explaining the problem for you now, that's okay. So omega is obviously a holomorphic one form on the set of all x and y belonging to x such that y is different from 0. Because we are dividing by y. If you're not in the 0 locus of y, the function is well defined, it's holomorphic. Inverse of holomorphic function is holomorphic, and just. But now the task here is to show that this actually extends to a holomorphic function to those points. What are the points where y is equal to 0? I mean, so at roots. At x equal to lambda 1, lambda 2, lambda 3. So these are 3 points which are bad points. Okay? So y is equal to 0. So what we have, well, your task in this case, and in general over the thing, your task is to show that actually you have this Riemann surface, non-compact, that's true. There are 3 points where your holomorphic one form is not originally defined. And you have to show that it extends to these 3 points in a holomorphic way. Right? That's the task. And how do you do that? Well, I won't tell you now, but that's it. But I mean, this is not just for 3. I mean, this thing works for degree n. For degree n, there are n points that are kind of bad points for this one form, and you just make sure that that extend to all. So, in fact, in this case, this is a basis. I mean, so what we know about it, so y2, for example, we check that y2 equal to p of x for the elliptic curve, degree of p equal to 3. We check that if you do projective compactification, you get a projective Riemann surface. And in fact, I wrote down an isomorphism to the C over lambda for some lattice using Weierstrass parameterization, right? So, and in fact, X can be compactified by adding one more point, right? So these two things come together and you get a torus of this one. You get X hat, which is isomorphic to C over lambda for some lambda. But I mean, this doesn't matter that this is actually isomorphic to that. We don't use it. But the thing is, this one form omega equal to dx over y is actually a basis for the space of holomorphic one forms for on this compact Riemann surface. In this case. So
omega is a generator.
Omega is a generator, yeah. And it's a one-dimensional space. It has to be proved, but that's the German. Exactly. But again, this is not just something in one dimensions. I mean, for genus one, I mean, you can take these hyperelliptic curves, for example. I mean, if degree of p bigger than 4, this is called hyperelliptic curve.
The genus of x hat is 1.
Sorry?
The genus of x hat is 1. What is the genus of x?
What is?
The genus of x.
Oh, X is not compact.
Mm.
So we cannot talk about this genus, unfortunately.
Oh.
I cannot. No, I mean, there are people who develop invariants, their own cohomology for non-compact spaces using L2 cohomology and stuff like that. But for now, there's no need. You take some bounds on at infinity, and then that gives you control. That's possible. Okay. Okay, so this is a little bit of exercise with this space of holomorphic one forms, and now we want to go to meromorphic one forms also, and then look at residue and residue theorem and this. Okay, so meromorphic one forms. Again, they are locally look like this. Look like omega is equal to, we can write f of z, dz, where this f is a meromorphic function on this u. F is meromorphic on u. Okay, so I mean, a point is called a pole. So I mean, this meromorphic one form. So poles of meromorphic one form. So there's a point P in X, and a coordinate neighborhood exists around it. U, a coordinate neighborhood around it, such that f of z has a pole at P. So f of z has a pole at P. Of course, then this omega, which is f of z dz, right? In local coordinates. So you just take a small enough coordinate on u minus P. I mean, you can use coordinate chart. You just write f of omega as sigma an zn, and from minus infinity to plus infinity dz. And now I can define the residue of this one form at the pole. Residue of, so the notation, there are different notations I can use, maybe omega at this pole P to be equal to a minus 1, where f of z is equal to this one. So we pick up the coefficient of z to the power minus 1, right? This is coefficient of z to the power minus 1. So you had this exercise. You were supposed to show that the residue of functions, of meromorphic functions on a Riemann surface is not a well-defined concept, right? So in other words, it's tempting to define, because in complex analysis, there are some bad habits that they teach you, or they teach all of us. One of the bad habits is to say that they tell us that you take residue of a function, right? The residue of function is not a good concept because it's not an invariant concept. It's not a geometric concept. We just say, okay, write it in this power series expansion and take a minus 1. But that's a very bad idea because if you change coordinate, you get something else. And that was part of your assignment. But the magic is that if you look at residue as residue of one forms as I'm defining now, it is actually a geometric concept and is independent of coordinates. So that's what we have to show. Okay, so let's now write the result then. So, I mean, because it's not obvious, if you just choose any other coordinate system, you're going to maybe get another answer. So whose coordinate is right? That's always the problem, right? In invariant geometric theories, we have to make sure. So let us then do a little bit of exercise here. Is independent of choice of coordinates. So, in other words, I have got something like omega equal to f of z dz in one coordinate, uz coordinate. Let's look at some case, for example, just to give us an example of how the calculation should be done. So let's take the case where omega, e.g., omega is equal to dz over z. In one coordinate system, you have it like dz over z. And obviously, in this case, what is the residue in this case? Right? Well, I mean, at p, obviously, just p goes to 0 here, and I've written this around 0. This is equal to 1, right? Now, let's change coordinates. Okay, when you change coordinate, you say, okay, z is equal to h of w. Now, this h is locally a biholomorphic map, right? Because it's a change of coordinate. So h of z is equal to z. I'm assuming I'm sending z to z, and h prime of z is different from 0 because it's an invertible holomorphic function. It has to be, since h is holomorphic, is invertible. I mean, it is holomorphic, of course, but it's invertible. Locally, I mean, it's invertible. It's a change of coordinates, right? So now let us write this one form in this coordinate w and see and calculate residue in that coordinate. In coordinate w, or omega. This is omega, should not be confused with w. You the same problem, right? Omega in coordinate w. Damn it, yeah. Yeah, okay, so now if you do that, you get omega is equal to, so maybe I'll have to do this. Omega is equal to dz over z, which is equal to d of h of w over h of w. Yes. Okay, now let's calculate this. What is this? This is equal to h prime of w dw, and in the denominator is h of w. Now, in the denominator, h of w, how it looks like h of w? It's a power series expansion of a locally invertible holomorphic function, right? So this should starts with a1, or not a1, I mean so some notation, I use b1w plus b2w squared plus b3w cubed plus so on, right? I mean, this is what it looks like. And this b1, we know what it is. What is b1? What is b1? Is the derivative of this h at 0. Yeah. So b1 is equal to derivative of h at 0. So let's write it. b1 is equal to h prime at 0. So now I have to calculate, so the problem is now to calculate the power series expansion of this around 0 again, around W equal to 0, right? So expand this. Near 0. Okay, so now if you want to expand this around that point, so let's see let's see what do we get here in this case. Okay, in this case, then I'm going to get something like this. I've got H prime of W, dW, and then I just factor W here. I mean, I just like B1W actually, times 1 plus B2 over B1, W plus B3 over B1 W squared, so on. Okay. Now, what do you think is the order of pole of this function at 0? I mean, what is the order of pole equal to 0 of this function? So the question is, how do you expand this function in power series in terms of W? Because that's what we have to do.
Could we expand out H prime of W as B1 plus B2 plus 2B2W plus 3B3W?
We can do that, yeah, but do we need that?
We can say 1.
Huh?
Is it 1?
What's it?
1? The order of
The order of pole is 1. And what is the coefficient?
B1. Oh,
Is it B1? If it is B1, then it's 1. Why? Because
Cos H prime 0 over B1 is 1.
exactly, absolutely. Yeah. So that's what you have to do. You have to evaluate this at 0. You get H prime of 0. You have B1W, and there is this mess, that's true. But this mess is completely harmless. Why? You see, the expression 1 over 1, so let's call this 1 plus G of W. You can use geometric series to expand it in terms of powers of W quite easily, and you see that this 1 over 1 plus GW is just 1 minus some mess, but that I don't care, but they're all higher order powers. It just starts with 1, and this B1 and this H prime 0 cancel, so this is really equal to 1 over W plus higher order terms. Which we absolutely don't care because that's what we need on this one. And that's the essence of well-definedness of residue of bond forms. Residue of bond forms. That's why residue of bond forms. Now, you should complain that, hey, you just checked it for dz over z. What about for general things? But for general things, they're exactly like this. My supervisor used to say in algebra, you just need longer papers, that's all. You don't keep calculating. Well, he was an analyst, so he didn't have patience for us. Yeah, indeed. I mean, actually, those things doesn't contribute. I mean, this is the essence of the calculation. So this is, you see why residual bond forms are just well defined like that, yeah. Okay, so I think it's a good time to stop, and then I will write down the residue theorem, and then we just go to discuss divisors. Because that's kind of a little more fun. I mean, this is interesting, but yeah, we get a little more fun there. Yeah. Okay, I'll just stop now. Yeah. And if you have questions, you can ask.